What is up, everyone? Welcome back to my channel. This is part 3 of chapter 1, and today we're getting a small intro into the worlds of acids and bases, one of the most fundamental and quite honestly mind-numbing topics in all of chemistry. Now, what is an acid? What is a base? Turns out the answer depends on who you ask. Two main theories here. Arrhenius theory, which is the older and simpler one, states that an acid is something that produces H plus ions in water. A base produces OH minus ions in water. So HCl in water creates H plus and Cl minus. That makes HCl an acid. NaOH in water yields Na plus and OH minus. That makes NaOH a base. Clean and simple, but limited since it only works in an aqueous solution. Now, Bronsted-Lowry theory is the one that AP Chemistry mainly focuses on. An acid is a proton donor. It donates H plus ions. A base is a proton acceptor, and it accepts H plus ions. This is broader and more useful. Under this definition, the definition still works in water, but also works in other contexts. When an acid and base react, the reaction is called a neutralization reaction. The acid donates its proton to the base, and typically you get water and salt as products. The acid and the base essentially cancel each other out. Let's look at two important cases. A strong acid plus a strong base, for example, HCl plus NaOH. Both of these dissociate completely in water. So in the completely ionic equation, every species is already split into ions, H plus AQ plus Cl minus AQ plus Na plus AQ plus OH minus AQ. Na plus and Cl minus are spectators, they don't do anything. The net ionic equation is just H plus AQ plus OH minus AQ yields H2O liquid. That's it. The essence of every strong acid, strong base reaction is just as a proton jumping from a hydroxide to make water. It's beautiful. Now, for a weak acid and a strong base like HC2H3O2 plus KOH, here's where it gets slightly trickier. Acetic acid is weak. It does not dissociate completely. So in the complete ionic equation, we keep acetic acid as an intact molecule, HC2H3O2AQ. KOH, being a strong base, does dissociate completely. K plus AQ plus OH minus AQ. K plus is a spectator. The net ionic equation is HC2H3O2AQ plus OH minus AQ yields H2O liquid plus C2H3O2 minus AQ. Notice the acetic acid is written intact on the left because it's weak and didn't dissociate. The OH minus is what pulls the proton away from it. The key rule here is that strong electrolytes are written as ions in net ionic equations. Weak electrolytes are written as intact molecules. Solids, liquids, and gases stay as intact formulas too. Alright, now here's an acid-base stoichiometry problem. Same process as precipitation stoichiometry, just use the net ionic equation mole ratios. Pause the video here and try to figure it out on your own. Ready? Alright, let's solve it together now. We're given 25 milliliters of 0.35 molar NaOH. What we want to find is the volume of 0.1 molar HCl needed. Step 1. The moles of OH minus is 0.025 liters, because we have to convert from milliliters, times 0.35 molar equals roughly 0.00875 moles OH minus. The next step is to write the net ionic equation. H plus OH minus yields H2O. The mole ratio here is 1 to 1. The next step, moles of H plus needed is about 0.00875 moles since the ratio is 1 to 1. After that, you want to find the volume of HCl, which is the moles divided by the molar, which is 0.00875 divided by 0.1, which is 0.0875 liters equals 87.5 milliliters. Notice that this is basically just M1V1 equals M2V2 for a 1-to-1 neutralization. But the net ionic equation approach is more general and handles cases where the mole ratio isn't 1 to 1, like sulfuric acid, which donates 2 protons. And now we get into one of the most important lab procedures in AP Chemistry, the titration. Before we go further, let me define all the key terms. Volumetric analysis is a method for figuring out concentrations by measuring volumes of solutions in a controlled reaction. Titration is the actual procedure. You slowly add one solution to another until the reaction is complete. The titrant is the solution you're adding from the burette. You know its concentration precisely since it's a standard solution. The analyte is the solution in the flask, the one whose concentration you're trying to find. The equivalence point is the theoretical point where the moles of titrant equal exactly the moles needed to react with the analyte. It's a perfect neutralization. The indicator is a substance added to the analyte that changes color when the equivalence point is reached, since it needs to visual signal when the titration is nearing its end. The endpoint is the point where you actually observe the color change. Ideally, the endpoint and the equivalence points are exactly the same. In practice, they're extremely close but not identical. Think of titration like this analogy. You're trying to fill a bucket exactly to a line. The water you're pouring from the hose is the titrant. The bucket is the analyte. The equivalence point is when the water is exactly at the line. The endpoint is when you notice the water hit the line and stop. Here are 3 things you need to know for a good titration. 1. You want to make sure you know your reaction. You need to know exactly what's reacting, and if you're doing a strong acid to strong base titration, you need to know that H plus reacts with OH minus in a 1-to-1 ratio. If it's a diprotic acid, meaning there are multiple hydrogens, the ratio is different. You need to do the stoichiometry. 2. Use the right indicator. Different indicators choose color at different pH levels. Choosing the wrong one means your endpoint doesn't match your equivalence point, and your result is wrong. Phenolphthalein is the classic. It's colorless in acid and turns magenta and pink in base. It's great for strong acid, strong base, or weak acid, strong base titrations. Rule 3. Use a burette to measure volume, not a graduated cylinder, not a beaker, a burette, the long, thin piece of glassware with precise markings and a stopper at the bottom. You read the burette at the bottom of the meniscus, and you can measure to 0.01 milliliters of precision. This precision is what makes titrations quantitatively useful. Here's a reference chart for indicator ranges. Obviously, you don't have to memorize this, because a lot of the time, if you're ever asked to find a specific indicator for a specific pH range, they'll give you like a few options. Each indicator changes color at a specific range, and you want to pick an indicator whose color change range includes the pH at your equivalence point. For a strong acid, strong base titration, the equivalence point is pH 7. Phenolphthalein works here. Although it changes around pH 8 to 10, it's close enough because the steep jump in pH at the equivalence point makes this okay. For other types of titrations, you'd pick something else. On the AP exam, you might be given a list of indicators and asked which is the most appropriate for a specific titration, like I just mentioned. The answer is to pick the one whose range overlaps with the equivalence point pH. Now this is a classic titration calculation, standardizing an NaOH solution using KHP. KHP stands for potassium hydrogen phthalate, and it's a very common primary standard, meaning it's a very pure, stable solid whose molar mass is precisely known. KHP has one acidic hydrogen, so it reacts 1-to-1 with NaOH. Given 41.2 milliliters of 1.3009 molar KHP, the analyte is 50 milliliters NaOH with an unknown concentration. Your first step is to find the moles of KHP. The molarity times the volume in liters is 1.3009 times 0.0412, and that's about 0.053557 moles. After that, the mole ratio is 1-to-1, so the moles of NaOH is also the same number of moles, which we'll call 0.05. Step 3, you want to find the concentration of NaOH, which is the moles divided by the volume. That's 0.05 divided by 0.05 equals roughly 1 molar NaOH. Notice the 4 significant figures throughout. This is precise standardization, so sig figs matter. Except in this case, where I'm just trying to get it done. And I don't want to have to say all the sig figs every time. But you know the idea. You get the idea. Now this one is a twist. Sulfuric acid, H2SO4, is a diprotic acid. It donates 2 protons. So the mole ratio is 2 moles of NaOH per 1 mole of H2SO4. The Ionic equation simplified is H2SO4 plus 2 NaOH yields 2 H2O plus Na2SO4. Or in net Ionic, it's 2H plus AQ plus 2OH minus AQ yields 2 H2O. But since H2SO4 gives 2 H plus per molecule, the mole ratio is 1 acid to 2 base. The moles of H2SO4 is equal to 0.02 liters times 0.245 molar equals 0.0049 moles. For the moles of NaOH needed, that's 2 times 0.0049 equals 0.0098 moles. The volume of NaOH is equal to 0.0098 divided by 0.61 equals 0.01607 liters, which is about 16.1 milliliters. The key thing here is to always write out the balanced equation first and identify the mole ratio. For polyprotic acids like H2SO4, the ratio is not 1:1. That's the AP trap. Now, I know this was a short video, and there's a lot more to acids and bases, but I'll save you from that struggle for a future unit, because here, ladies and gentlemen, is where I'm putting a pause on our journey together. Once again, thank you so much for watching, and for those of you who stuck around till the end. If you learned anything from this video, or you're just excited to get into our next video on redox reactions, then make sure you hit that subscribe button and drop a like if it's not too much trouble. And I'll see you guys next time.